So we're going to look at limits, and we're going to look at limits from an intuitive sense. There is a formal definition, which we're not going to look at, but our intuitive definition is as follows. We're going to say that the limit as x approaches a for some function f of x equals a specific value, a real number, if we can make the value of f of x arbitrarily close to L by taking x values sufficiently close to a on either side of a, but not equal to a. So that's your definition in intuitive sense, and let's take a look at graphically and see what that's looking like. So here's a function f of x, and it's got a it's not defined at x equals 3. X equals 3 of a whole in this function. Nonetheless, I want to say that the limit as x approaches 3, what do I expect to get as x gets closer and closer to 3 from either side? As my x values from the right side, the positive side, get closer and closer to 3. As my x values to the left get closer and closer to 3, I expect to get to 4. And as a matter of fact, I can pick numbers really, really close to 3, and the closer I pick numbers to 3, the closer my outputs get to 4. So if I want to be within a certain tolerance of 4, there's some numbers down here I could pick close to 3 on each side that would give me outputs that close with that tolerance to 4. So we say here the limit as x approaches 3 of f of x equals 4. Now note, the function is not defined, f of 3 is not defined, but the limit is. So if we take a graphical approach, we can answer some limit questions pretty quickly at times. Looking at the first one up here, the limit as x approaches 3 of this linear function 13x, I know what I'm looking like. It's a line, slope's 13. As I approach 3 from either side, I'm going to approach an output of 39, and I'm done. Second one, the limit as x approaches 2 of 2x squared plus 1. I know that's a parabola. It opens up. Its y-intercept is 1. What do I expect to get as I approach 2? Closer and closer to 2 on either side. I'll expect to get 2 squared is 4. 4 times 2 is 8. 8 plus 1, I'll expect to get 9. How about, again, graphically, as x approaches pi over 2 for sine x? Well, I know what the sine graph looks like. It starts at 0, it goes up to pi over 2, gets up to 1, so I'm looking here at a value of 1. I can get closer and closer to pi over 2 on either side, and I'll expect to get an output of 1. How about the function, the absolute value of x over x? Well, here, I can't plug in a 0, because if I plug in a 0, the function is undefined. And again, up here we evaluated. We actually plugged our values that x was approaching into the functions. We were able to do that because all three functions' graphs up here are continuous in that the graphs can be drawn without lifting my pencil from the paper. So if I know that the function is defined everywhere, its domain is the set of real numbers, then sure, the function, I can simply plug in this x value and my output will give me the limit that I'm looking for. However, this function down here, I don't have, I can't plug in 0. What does this function look like? Well, for all positive numbers, it's going to be the absolute value of, say, 2 over 2 is going to be 1, and the absolute value of any number over itself is going to be 1. So I'm looking here to the right side then. I'm looking like this. What happens if I put in negative numbers to the left? Absolute value of, say, negative a half is a half. So half over negative 1/2 is negative 1. So for all negative numbers, I'm going to look like that. So this is at 1. This is at negative 1. Now, as I approach 0 from either side, do I expect to get the same number? And the answer is I don't. I expect to get 1 coming from the right side. I expect to get negative 1 coming from the left side. So this limit here does not exist. So another notation for limits, we could say, and I would read this aloud as the limit as x approaches a of f of x equals L. I can say f of x approaches L as x approaches a. So that would be the same thing. My function outputs are approaching L as x gets closer and closer to a. Now we're going to look at some tougher examples, and again they're tougher because you can't just plug your value, the x value that you're approaching, into the function because the function isn't defined for that x value. It means I've got some sort of hole or discontinuity at this value. So then I got to use my brain and think. what is this function? And one way to think is think graphically. What does this thing look like? X minus 1 over x minus 1. Well, that simply is going to be 1 for every value other than at x equals 1. So it's going to look like this horizontal line with a hole here at x equals 1. Outputs are always going to be 1 everywhere except at 1 where the thing's not defined. So what do I expect to get as I get closer and closer to 1? I expect to get an output of 1. So we say, indeed, the limit as x approaches 1 of x minus 1 over x minus 1 equals 1. Same situation here for this one. I can't plug 1 in, because if I plug 1 in, I get my denominator 0. I can't have a 0 in the denominator. What does this graph look like? Well, I see a difference of squares, so the first thing I'm going to do is say, I wonder what happens here if I go ahead and look at this a little differently. Look at this as x minus 1 over x plus 1. And indeed, what's going to happen for any value other than 1, what's going to happen to those two factors in the numerator and denominator? They'll cancel. So for all values other than at exactly 1, this function here, x minus 1 over x minus 1 plus times x plus 1, will be equal to 1 over x plus 1. So let's look at the limit as x approaches 1 of 1 over x plus 1. Now I can go ahead and say, let's evaluate that by plugging in 1 directly, and I get 1/2. Again, same situation here. I'm looking at, I can't plug a 0 into my denominator here because that would give me a 0 in the denominator. No go. So this one is particularly tricky because I look and say, well, as I get closer and closer to 0, this square root up here is going to get closer and closer to the square root of 9, which is 3. And let's see, 3 minus 3 is 0. So I'm heading closer and closer to 0 for my numerator. Heading closer and closer to 0 for my denominator. Geez, maybe, I have no idea. It's getting closer and closer to 0. I don't know. Trick for this one. You guys have been rationalizing denominators for a long time. We actually want to rationalize a numerator here. And my algebraic trick here is to multiply the top and bottom of this by the square root of t squared plus 9 plus 3 over the square root of t squared plus 9 plus 3. And you might say, why am I going to do that? Well, watch what happens when we do that. In the numerator, then we're going to get a difference of squares. And we know our difference of squares, a minus b times a plus b, will be a squared minus b squared. So we know then that this is going to be the limit as t approaches 0 of t squared plus 9, that's the a squared, minus b squared, which is 9, all over t squared times the square root of t squared plus 9 plus 3. And I go ahead and simplify that some more because I can see that the 9's are going to cancel each other out up here, so I get the limit as t approaches 0 of t squared over t squared times the square root of t squared plus 9 plus 3. And now I look again and I note that the t squareds are going to cancel, so I get the limit as t approaches 0 of 1 over the square root of t squared plus 9 plus 3. Now I can go ahead and evaluate directly by plugging in a 0 for t squared, because then I've got a nice friendly non-zero denominator here. So let's see. 0 square root of 9 is 3. 3 plus 3 is 6. So my limit here is 1/6. Not really obvious from looking at this at first glance. Finally, another way we look at limits is at times an algebraic manipulation can't do. We're going to look at some problems where you're actually going to have to pick up your graphing calculator, look at the graph, and make sense out of the graph. Maybe look at a table of values as you get closer and closer to your limiting number here and see what the calculator tells you. Warning, at times the calculator will do good things for you, and other times it won't. So in this case, the calculator will do good things for you. So if you go ahead and look at the graph, plug into y1, sine x over x, make sure you're in radian mode, and look at the graph as x approaches 0 and see what you get. So up till now, we've kind of intuitively talked about the limit as approaching, as I look and approach my limiting value from both sides, and we've talked about that. We are going to also need to talk about one-sided versus two-sided limits. And we actually formalize approaching from the right side by saying as x approaches 4 from the positive side, as I approach 4 from the negative side, we formalize that in our notation by x approaches 4 from the left. We would say x approaches 4 from the left, x approaches 4 from the right. And for this question, to answer that, I've got a graph here. What is my limit as x approaches 4 from the right of f of x? As I approach 4 from the right, what do I expect to get? I get closer and closer to 7. What do I expect to get as I approach from the left? I expect to get closer and closer to 7. So the two-sided limit then, the limit as x approaches 4 overall for f of x would be 7. Let's take a look at what happens at negative 3. As I approach negative 3 from the right, what do I expect to get out? I expect to get out a 5. And what happens as I approach negative 3 from the left? I expect to get out a 3. So we say the left-hand limit and the right-hand limits as I approach, as x approaches 3, are different. They're 5 and they're 3. And therefore, overall, we would say the limit as x approaches neg 3 overall of f of x does not exist, because the left-hand limit and the right-hand limits are different numbers. So again, to formalize that here in writing, we say the limit as x approaches a of f of x equals L if and only if, so this is a definition, if and only if the limit as x approaches a from the right of the function equals the limit as x approaches a from the left of the function. That's a definition. Note the if and only if means it goes both ways. If the limit as x approaches a of f of x equals L, then both two-sided limits exist and are the same number. Or if both left and right hand limits exist and equal the same number, then the limit as x approaches a overall will equal L. Last little introduction here on limits, and I talked in the first slide a little bit about continuity. We're going to say that a function is continuous at some point if and only if the following conditions are upheld. The limit as x approaches a, the two-sided limit of f of x, has to equal some value, some real number, and the function has to be defined at that value a and have that same output value. So two things. The limit overall has to exist, the two-sided limit has to exist, and the function has to take on the value of that two-sided limit there. Let's look at some examples. So in the first case here, if I wanted to look at the question would be, is this function g of x continuous at x equals 3? And the answer would be, well, the limit as I approach 3 from the left and the limit as I approach 3 from the right, those are the same value, 5. So the limit as x approaches 3 overall exists and is 5. But g of 3 does not equal 5. G of 3 equals 7. So we say this function is not continuous at 3. And a continuous function intuitively is a function that I can sketch without picking up my pencil from the paper. That is on the domain, in the function's domain. If I can sketch it without picking up my pencil from the paper, we'll say it's continuous. And in order to graph this function, I'd have to pick up my pencil, come up here, put that point, the value of the function at 3 is 5, and then put my pencil back down, so not continuous. How about this function down here? Let's call this function here, we'll call it t of x. If I look at t of x, the limit as I approach 3 from the left is different from the limit as I approach 3 from the right. We're done. We already say the function is continuous. And we have names for types of discontinuities. We say this is a removable discontinuity because it's a single point that I could fill in. We say this is a jump discontinuity because I've got a jump. As I approach from the left, I'm expecting to get 5, but then I jump. As I'm approaching from the right, I expect to get 7. So that's called a jump discontinuity.